Hey everybody, it's Mr. Bliss. This video is part 2 of a series of videos on electron configuration. Our first video focused primarily on the Bohr model of the atom, the planetary model of the atom. This second part gets a little bit deeper into the nitty-gritty of how electrons actually do fill in atoms to give you a more realistic depiction of what an atom looks like in real life. So here we're going to be talking not just in a 2D space like the Bohr model, but in a 3D space. So our Bohr model, we talked about, let's turn this on. We talked about electron shells. And with electron shells, you essentially had your nucleus, and then you had these circular or spherical shells where an electron could exist. We call this the first shell, the second shell, and the third shell. There are more, but we only got up to the third shell. This is useful, but it's not entirely accurate. So here we're going to be looking at a 3D model. And with a 3D model, the big difference is that we're not just going to be talking about shells, we're going to be breaking it down into smaller components that we're going to be calling subshells. And our subshells, obviously sub meaning below, we're going to have 3 types. So we're going to have an S subshell, a P subshell, D, and F. However, for this course, we are not going to be focusing on D and F. That's going to be for DP or higher level chemistry if we get into it. So with subshells, subshells can be further broken down into things called orbitals. We'll talk about that just a little bit, but we're not going to get into it quite yet. So a reminder, we're going to be talking about 3D space here. So when we talk about 3D space, okay, you have to remember that you have an X and a Y, and you also have a Z that kind of comes straight right back at you. And I know that in math you might relabel these axes in a different way, but the main point here is that there are 3. So if you think about the way that electron clouds are, they occupy a 3D space, and they actually occupy them unevenly. They're not all spheres. They exist in these shapes that we refer to as orbitals. So this picture right here shows some of the ones that we're going to be talking about. We're going to be talking about these S orbitals, which are spherical. It's a good way to remember it, actually. S can stand for sphere, like this. This is an S orbital. And then a P orbital is actually made up of all 3 of these. So what does a P orbital look like? Well, it's kind of hard to say, but if I did it using this, this XYZ axis, I would first draw in my X here, which looks a little bit like a dumbbell, on my Y, which would go this way, and then my Z, which would come in this Z axis like this. So it's a 3D space like that. Now, with an S orbital, which is this sphere right here, can hold 2 electrons, and each one of these can also hold 2 electrons. So a P orbital, which again looks vaguely like this, can hold 6 electrons. With our D and F, D can hold 10 electrons, and F can hold, I think it's 14. I might have to Google that, I apologize. But we're not going to be dealing with them too much. Now, what do a D and F orbital look like, or subshell look like? Well, they're really complicated. They look a little bit like this. In order to understand them, we have to do some real serious geometry. We have to do some real serious chemistry. So we're not going to worry about it too much. So let's get into it. Again, we have our periodic table here, and we're just going to do a couple of quick examples just to show you the difference between the Bohr model and this kind of quantum model with subshells. Let's do the electron configuration of carbon. Just because we love carbon, because we're going to be doing it a lot in biology. If we were going to be using the Bohr model to explain the electron configuration of carbon, we would do it this way. We would write in the nucleus with 6 protons and 6 neutrons, and then we would start filling it in just as we did before, with our first shell holding a maximum of 2 electrons, and then our second shell filling in our electrons like seats on a bus, like this. And that has a total of 6 electrons. 4 valence electrons, 4 electrons in the outer shell, but 6 total. When we start getting into this new depiction, this 3D depiction, it gets a little bit more complicated. Rather than just saying, well, in the second shell it holds 4, we have to break that down into its subshells. So let's do it. In order to understand how we fill in these sequences of subshells, we have this really useful little diagram here that's called the diagonal rule. And it looks a little bit complicated, but it's really not. You just write in your 1s here, and then you just go up in your electron shell number as you go down this table. And then you come over, 1 down, and you start at 2, and you fill in your p's. 2p, 3p, 4p, 5p, 6p, and then you come down and over again for your d's, and then down and over again for your f's. But to keep things really, really simple here, remember, we are not worrying about our d's and f's. So, and we're not even really going to be worrying so much about these either, so don't worry about that. Okay. So we were doing carbon here. Let's do carbon again using this other method. We're going to start in the top right hand corner up here of our diagonal table, and we're going to follow the arrow, which is exactly the way you do it for any other atom here. So you're going to come down, and the first subshell that we come across is 1s. Well, why is it 1s? Well, 1 refers to the electron shell, the first shell. S refers to the subshell that we're using, the shape of the subshell. And then what we're going to do is we're going to write how many electrons are in that subshell. Well, with our 1s subshell, it is full. It has 2 electrons. Remember, this isn't very well written here, but an s subshell can hold 2 electrons, a p subshell can hold 6. So first we have our 1s here, and then after we get to this arrow, we're going to come to the next line. We're going to keep going. And we have 2s, which makes sense, right? Because before we had our first shell that has 2, and then you come to your second shell. So we have 2s, second subshell, s orbital. Well, an s orbital can only hold 2, so we've already filled it. Then we're going to come to the top of this over here, and we're going to come across our first p orbital, which is our 2p. We call it 2p because it's in the second electron shell. So we're going to write 2p. Well, how many electrons do we have? We know that we can fill 6, but it's not going to come all the way to 6 because we only have 6 electrons total. So how many more do we have? Well, here's 2, here's 4, and we only need 2 more, right? And that gives us carbon. This is our electron configuration of carbon. Another way that we can write this, instead of writing 1s2, 2s2, 2p2, is we can do a shortcut and we can write whatever our last noble gas was. It's a little bit confusing, but we would do it like this. We would write it in brackets, helium, which is here, and then how many additional electrons you have? Well, you have your 2s2, and then here's going to be your p, and you only have 2 in there. So you have helium, 2s2, 2p2. Now, this seems a little bit confusing, but the more you do it, the more you can see this pattern here. So we're going to do another one. I'll even erase this. You can pause it and copy it if you need to, but we are going to go a little bit further, and we are going to do, let's do magnesium. Okay. Let's do magnesium, which is 12 on the periodic table. So we're going to have 12 electrons that we need to deal with here. We remember that the electron shells correspond to the period. So we know that we're going to use up our first electron shell with hydrogen and helium, and then we're going to use our second electron shell here, and we're going to get into our third electron shell. So we should get into the numbers where it starts to say 3. But let's look at what that actually looks like. We're going to start off with 1s, 2, because that gets filled this way. We're going to come this way, 2p, or sorry, 2s, 2, which gets filled. We're going to fill our 2p with 6, and we're going to keep going to our 3s. Well, once we're in our 3s, we're only going to put 2 electrons in it, just like that. So another way of writing this, so we're done. Another way of writing this, rather than going to the process of writing 1s2, 2s2, 2p6, because that's going to be the same for any atom after this, is we can use that noble gas depiction. So our last noble gas here was neon, so we're going to write neon 3s2, just like that. Hopefully that makes a little bit more sense to you. I know that it's a little bit complicated, but it's just a way of visualizing how the electrons would actually fill in a three-dimensional space. They wouldn't just fill in a shell like this, they would actually take on a three-dimensional shape, just like this picture in here, where you would get s orbitals and p orbitals that is more realistic. So let me know if you have any questions, and I will do my best to answer them. All right.